Guenach. I'm from imec, Belgium. Thanks for giving me the opportunity to talk today. Well, regarding your first question, our main goal in this work package 6 is to validate some theoretical concepts developed in work package 5 and the underlying AI-based signal processing developed in work package 4 for some components. The main targets are to assess the sub-terahertz link robustness to RF non-idealities, which is actually very challenging at this frequency band, and this is in fact very important to risk the transmission of radio communication in such challenging frequency band where abundant spectrum is available for high-speed links. So the second main concept is the trustworthiness concept, mainly the hardware fingerprint, where various RF devices, they have different signatures, and we want to exploit these signatures to identify or certify these RF components under the test. How are we going to do that? In fact, we have developed theoretical concepts, link level simulators in other work packages, and we are complementing these five models with real measurements. So actually our approach in this validation work package is mixed approach, where we have software tools or link level simulators that we are complementing with real hardware measurements. So it's mixture of software and hardware components, what we call hardware in the loop. So yes, then we have foreseen, in fact, for this three different proof of concept covering wider range of spectrum, going from the sub-6 GHz all the way to the sub-terahertz spectrum. So as I mentioned, we have three different proof of concepts covering wider range of spectrum from different partners. So the first proof of concept is sub-6 GHz. Proof of concept goal there is to be able to identify devices, RF devices from the same or different manufacturers. And I will give the floor to my colleague Florent from Ericsson to give probably more details on the progress for this sub-6 GHz proof of concept.
Yeah, thank you, Mamoun. In this task 6.1, what we are trying to do is to apply the concept we developed in work package 5 and work package 4 for the identification of devices based on the radio frequency fingerprinting with an accuracy of 80% for devices from the same manufacturer. For this purpose, we are doing two things. First, we are using active radio frequency fingerprinting techniques that we developed in-house that are enabled by our use case, that is cellular communication, and in particular 5G and beyond. We also developed a hardware experimentation platform based on software-defined radios and using a real 5G radio signal.
Thanks, Florent, for this this general overview on the activity regarding the hardware fingerprint to identify RF devices from the same or different manufacturers with different accuracies using the neural networks developed in work package 4. For this first experimental setup, there is quite some impressive progress there, and some of the work will be demonstrated in the plenary meeting. The second proof of concept is sub-10 GHz, where actually the target there is to use the hardware fingerprint in the presence of manufacturing spread or manufacturing variation. So manufacturing variation meaning that when you are fabricating the same chip or component in the fabrication process, it's never perfect, and there are of course variations. So this experimental setup from NXP is targeting mainly the power amplifier, the duality power amplifier, widely deployed in base stations, in 5G base station. And so we will see to which extent the neural net, the AI-based signal processing developed in work package by Ericsson, work package 4 by Ericsson, will be able to still certify this device under the test with this manufacturing variation. So there has been already some good progress. Some preliminary data from the software tool developed by of NXP has been delivered to Ericsson to do the validation, the certification of the device or authentication of the device. So this in fact highlights the importance of the collaboration between the different partners, which is key in these projects. The third proof of concept is the sub-terahertz proof of concept, targeting where we aim, as I mentioned previously, this is from imec, to see to which extent we can control the RF non-idealities in the terahertz band, which is challenging, and to de-risk these frequency bands with very high spectrum or available there. So far, we have made very good progress. We have developed a full-blown link level simulator with representative hardware impairments in the terahertz band, different RF beamforming architectures, different channel models going from stochastic to geometrical channel models, and so on and so forth. So this link level simulator developed in Work Package 5 now is being extended by RF components, and for this purpose, imec had some IC design at D-band, and this IC design, of course, is outside the development of this design is outside the scope of this project. So the performance validation of the chip characterization has been successfully done, and also it's not part of this project. Then we managed to integrate this IC design with the link level simulator from the Work Package 5 I mentioned previously, and this has been successfully integrated. And now in this plenary meeting we will show some interesting features like beam steering or beam alignment capabilities of the full transceiver. I think that's all. That covers more or less the progress in the work package or in task 5.1 of this validation, this work package on the validation. And overall, very good progress, very good collaboration with different partners. We're exchanging data, and we are. This is actually in good shape. Thank you.
Today in Frankfurt, we'll be demonstrating two very important key use cases. There is the first use case. It's about the successful authentication of devices from the same manufacturer, even for devices that are from the exact same model. This is a scenario that we refer as a closed set scenario when it comes to the machine learning, meaning that the machine learning models has been trained with data from all the devices which will be that we test. So even for identical devices, we managed to have more than 90% accuracy, which is pretty nice, and validating the KPIs we had in the project in this task 6.1. Then we go a step further, and we will demonstrate how to uncover an unknown devices trying to perform an impersonation attack. This is what we refer as an open set scenario, as obviously for the machine learning, the attacker is not part of the training data, but becomes later performing what we call a replay attack. So the attacker will record the signals from a legitimate device between the legitimate device and the base station, and then we replay the exact same signal to try to get access to the network. In here, we saw that when we attack with a device from the same manufacturer but a different model, we can very easily and have very good results in uncovering such an attack. However, what we observed is when the device attacking is the very exact same model than the legitimate device, it becomes way harder for the machine learning model. So this is a work in progress. We are doing very good progress right now, and we are sure that we can tackle this challenge. So it's very exciting. We still have 1 year to cover, but I think we will come up with very innovative solutions within its field. Thank you.